So in 7.7, we're going to be focusing on the idea of approximate integration. So up until now, to do all of our integrals, we've pretty much been using the fundamental theorem of calculus part 2, which tells us that if we can find an antiderivative of a function f, we can evaluate its integral by using f of b minus f of a, right? And we interpreted that geometrically as being the area underneath the curve. Well, it turns out that we're going to have need to be able to integrate things that don't have antiderivatives. So enter the idea of approximate integration. So the two main applications of approximate integration is that first one, when f does not have an elementary antiderivative, and two, the function f is determined from a scientific experiment. So if you're out in the field gathering data, you're not going to have a nice function f for which to take an antiderivative, right? So imagine you're out, you've got a telescope, and you're observing the acceleration and velocity of some satellite that comes flying by, right? And if you want to find something out about that, you might need to integrate or differentiate said data set. Well, as I said, we don't have a function, we have a discrete set of data. So how can we do those types of operations? So these techniques have many applications, and we'll just touch on the very tip of a giant iceberg. If you're more interested in this, you should look into a class called Numerical Analysis, which is really the idea of this in general. So for those of you that are going on to engineering and other such things, you will most likely see some of these classes in your not too distant future, probably under an EGR prefix as opposed to a math prefix, but at the end of the day, it's all about the same. All right. So that leads to a couple of things that we know from the past. So in Calc 1, before we actually learned the fundamental theorem of calculus, we approximated some integrals by using Riemann sums, right? And we had a couple of different ways we could do that. We had the left Riemann sum, so we used the left endpoint. We had the right endpoint. And then we also used a midpoint formula as well for finding the area underneath the curve. And each of those turns out is an approximation, sometimes more accurate than others. And we'll talk about the accuracy of each of these as time goes on. So let's go ahead and get started looking at the trapezoid. So the idea with the trapezoid rule is as follows. So before we talk about the trapezoid rule, let's remind ourselves about a little bit of vocabulary. Well, what is a trapezoid? A quadrilateral, that is correct. And it's a very specific type of quadrilateral. Indeed. So the definition of a trapezoid is a four-sided geometric figure with exactly two parallel sides. So to remind us, if I were to have, say, something that looked like this, this would be an example of a quadrilateral, and specifically a trapezoid. So if we talk about the distance between the parallel sides, we will refer to this as the height of the trapezoid. And then it's going to have two things we will refer to as the base. So we'll call this base 1 and symbolically b sub 1 and base 2. Turns out the area, which is what we're going to be interested in, of a trapezoid which we will denote a sub t, is equal to 1/2 times base 1 plus base 2 times its height. Or in other words, if you average the heights of both the bases and then multiply by the perpendicular distance in between them, you end up with the area of said object. And you can figure that out in a few different ways, but we're going to just assume it's true for now. All right, so now armed with this information, let's go ahead and see what the trapezoid rule is all about. So I have some curve, and I have A, and I have B, and if I want to find the area underneath that curve, that's going to be this, and all of these pieces. So then we could approximate it by creating a partition where A is denoted by x0, and then we would have, say, x1, x2, all the way out to the end where we finally get to B, which we would call xn. So now let's focus on one of these rectangles. So if I have my parallel sides here, and in Calc 1, as we mentioned, we did both the left endpoint, which would be that. We did the right endpoint, which would be an overestimate, which would be this. And then we also did the midpoint, which might be a little better. The idea of the trapezoid rule is, well, how about I just create a line segment that goes from one end of that rectangle to the other? That's going to be a better approximation than either of the perpendicular approximations we used before, right? So it's going to help us get a more accurate representation of each of these. So I have my first area, A1, and then I could do the same thing here, A2. And I could keep doing this all the way to the very end where I get this, and I connect finally my last two pieces, and that's going to be AN, right? So let's see if we can figure out what a formula for the sum of all of these areas is. So the first thing we're going to note is that the heights of each of these, for the left side, it's going to be f of x0, or f of a. This second height is going to be f of x1. This height's going to be f of x2, all the way out to f to the xn minus 1. And the last height is going to be f x sub n. So then A1, according to our formula for a trapezoid, is 1/2 base 1 plus base 2 times our height. So we're going to have to turn this around a little bit. I'm going to call this base 1, and I'm going to call this side base 2, and my height is going to be the distance between those parallel sides, right? So according to this then, the area of the first trapezoid is 1/2 base 1. Well, base 1 is f of x0 plus base 2, which is f of x1, times the distance in between them. Well, that's the distance from x0 to x1. Well, that's going to be our partition delta x that we used from Calculus 1, right? So the distance between each of these And recall, delta x was b minus a divided by n, right? The distance for each of these. So that would give us a1. Then what would a2 be? Well, the same thing, 1/2, but now I would do f of x1 plus f of x2 times delta x. And then I could keep going. What would a3 be? Well, 1/2 f of x 2 plus f of x3 times delta x. And I could keep going. So finally, a sub n minus 1 is going to be 1/2 f of x sub n minus 2 plus f of xn minus 1 times delta x. And then finally we get to our very last rectangle a sub n, and it's going to be 1/2 f of xn minus 1 plus f of xn times delta x, right? For all of those different ones all the way till we get to the very, very end. So now, if we were to look at all of these, the first thing we'll notice, what do all of a1, a2, a3, all the way out to an, what do they all have in common? So we have a common factor of 1/2 and a delta x. So my area total is going to equal 1/2 delta x, or delta x divided by 2. And then what's going to be left inside? Well, I have to add up all of these things. Well, notice that for most of them, I have an f of x1 and an f of x1. And then I have an f of x2 and an f of x2. And then I would have an f of x3 and f of x3. And so forth. I would continue this pattern till I get to here. And as a matter of fact, all of the other ones in between would have corresponded with something. So how many of all of the interior numbers am I going to have? 2, right? Because they occur in pairs, except for the first one and the last one, right? So we're going to have f of x0 plus 2 f of x1 plus 2 f of x2 plus ... all the way out to f of x sub n minus 1 plus f of xn, and that's going to end what we have. So that's our total area. So we want to write this in a slightly more compact way. So writing it in sigma notation, we have delta x divided by 2. We could write this as f of x0 plus f of xn plus sigma as I goes from 1 to n minus 1 of 2 times f of x sub n. And that would be our trapezoid rule, right? Because we add all the ones in the middle twice, except for the first one and the last one. And we get something that looks like this. All right, so this is our trapezoid rule. So let's go ahead and use this thing to get what we get. So it tells us, typed out it looks a lot nicer than my hand-drawn one, but we get this same deal, what we just derived above. Without the sigma notation, we'll see we will like the sigma notation to help us do some of these things. So the integral from a to b of f of x dx is approximately equal to t sub n, which is the trapezoid rule using a partition of n, And we have delta x over 2 plus the sum of all of those fun things. All right. So to use this formula, we need to calculate delta x. So delta x is equal to b minus a over n. So in this case, our integral is from 1 to 2, so our b is 2, our a is 1, and our n is given as 5. So this gives us that delta x is equal to 1/5. We then need to know what our partition is. So if we come back and look at our graph, our partition starts at A and ends at B, and A is going to correspond to x sub 0, and B is going to correspond to x sub n. Our formula for our x sub I, the sequence of x values, is A plus I times delta x, where I is going to go from 0 to n. So plugging into our formula, x sub I is going to be 1 plus I times our delta x, which is 1/5. So we get 1 plus I divided by 5. And it's worth noting, if I calculate x sub 0, I get 1 plus 0 over 5, which equals 1. That's my a value. And if I calculate x sub n, which is x sub 5, I get 1 plus 5 over 5, which is 5 divided by 5 is 1. And 1 plus 1 is 2. And that's my b value, right? So essentially, if we were to draw a picture of what's going on, if this is 1 and this is 2, we're going to have, this is our x sub 0, x1, x2, x3, x4, and x5, right? So our partition is going to be dividing the number line into these distinct pieces. And we want to find the integral of 1 over x. So using that same type of scale, there's 1. Our graph would look something like this, and then with 2 it would decrease to a half, so it's going to look something like this, right? So our approximating trapezoids are going to be something that looks like this. There's our A0, A1, A2, A3. Oh, I needed to start at 1. A1, A2, A3, A4, and A5, right? Because we're going to have 5 rectangles, but we're only counting, remember we're double counting all of the interior sides, because this side is a rectangle for both A1 and A2. This next side is counted twice because it's a side for rectangle A2 and for rectangle A3. The only 2 that are counted once are the 2s on the outsides right here. They're only counted one time. All right, so now we have our stuff. This picture isn't needed. We want to use our formula. Our formula says that the integral is approximately equal to t sub 5, and t sub 5 is equal to delta x divided by 2. Well, we have delta x, which is 1/5, divided by 2, and then we multiply it by f of x0 plus f of x1 plus f of x2 all the way out to these. So we have f of x0 plus 2 f of x1 plus 2f of x2 plus 2f of x3 plus 2f of x4 plus f of x5. So if we wanted to, we could calculate each of these manually, right? So x0 is 1, x1 is 1.2, x2 is 1.4, 1.6, 1.8, and 2. So then this would be 1/5 divided by 2 is 1/10 times f of 1 plus 2 times f of 1.2 plus 2 times f of 1.4 plus 2 times f of 1.6 plus 2 times f of 1.8 plus 2 times f of 2, right? You're probably already getting sick of writing this down. There was a reason we did all of those calculations at the very beginning. So the first thing we might want to take note of is we have all of these values, and let's grab our graphing device and work through this. And we'll do this a few different ways. So let's do it the longer way first. So we would start with our fraction, and we had delta x, so another fraction, 1/5 divided by 2, and then times, oops, got ahead of myself, I need to put my function in. So what was the function we are integrating? 1 over x dx. So 1 over x. So let's go with 1 over x. Now back to our home screen. So we have our delta x divided by 2, and now we need to put in these values. So we would go alpha trace, choose y1 of 1, plus alpha trace, oh, I hit enter too soon. So plus 2 times alpha trace y1 of 1.2 plus 2 times alpha trace y1 of 1.4 plus 2 times alpha trace y1 of 1.6 plus 2 times alpha trace y1 of 8 plus finally, just alpha trace no 2 this time, y of 2. Close our parentheses and we hit enter, and what do we get? This is our approximation. So, a couple of observations. That wasn't terribly hard. The n was only 5. So if I had to write this out for, say, n equals 20, what do you think the probability is that somewhere in that madness I make a typo? Probably pretty good. I mean, I'm going to be honest, I probably would at some point. So we want to try to find a way to make this a little more efficient. That's where the sigma notation comes in. So let's rewrite this using that sigma notation that we talked about up here. So we noted that we can do all of these guys together. So it would be 1/10 times f of 1 plus f of 2, and then plus 1/10 times the sum, as I goes from 1 to 4, of f of x sub I. Let's focus on this bit first in our calculator. So we have 1/10, and then to get our sigma, we go alpha window, and we choose choice number 2, and then we're going to have I go from 1 to 4 of 2 times, so we go 2 alpha trace y1, but then we need to put in our x sub I. Well, what was our x sub I? 1 plus I divided by 5. So we're going to type that in. 1 plus I divided by 5. Close our parentheses, and we have another parenthesis. So that gives us this value right here, right? I did it right on the calculator, but I left the 2 off up here in this formula. Should be a 2 right there, right? So that's our correct value for this. And now we need to figure out this. Well, it's just 1/10 times each of these. So if we just press plus, it pulls down our previous answer, plus 1/10 times y of 1 plus y of 2. And we get, when we add them both together, we get the same value that we did when we did it manually, right? So being able to write these things in sigma notation will help us get the answers, especially if n starts getting bigger. You can always type them out one at a time by hand, but it's a giant pain. You really don't want to do that, right? So we'll talk about some different strategies on how to do this as we go forward. But at the end of the day, that's the basic idea. We're going to approximate an integral by creating, in this case, trapezoids, right? First thing we're going to calculate is delta x, which is b minus a over m. So 1 minus 0 over 4 gives us 1/4. And our x sub I is going to be a plus I delta x. So 0 plus I times our delta x, which is 1/4. So we're going to get I divided by 4. So then, in terms of what we're going to have then, is we have our formula, which is delta x. So 1/4 divided by 2 times our first thing. So that's going to be y of 0 plus our last thing, y of 1, plus the sum as I goes from 1 to 3 of y of I divided by 4 times, no, nothing, we've already taken care of it. So now we're going to put this in our calculator. The first thing we do is we put in our function for y, which is 4 over 1 plus x squared. And we start typing. So alpha y equals 1 over 4 divided by 2. In parentheses, alpha trace y1 of 0 plus alpha trace y1 of 1 plus, and I did it again, 2 times, right? That's why we had to break up the sum. Trapezoid rule has a 2 in it, so don't forget this 2 when we put in our formula. And then we go sigma, alpha window, our sigma notation as I goes from 1 to 3 of 2 times alpha trace y1 of I divided by 4. Hit enter, and we think for a second. Our calculator gives us this value. We get a rational function, so let's hit math and choose decimal. And what do we get as our approximation? Our calculator gives us 3.13. So the question might become, well, how accurate is that? Well, in this case, we can actually calculate our integral. If I pull my 4 out of the integral, I'm left with 1 over 1 plus x squared dx. Well, the antiderivative of 1 over 1 plus x squared is the inverse tangent of x. And we evaluate that from 0 to 1. So that's 4 times the inverse tangent of 1 minus the inverse tangent of 0. The inverse tangent of 0 is 0, and the inverse tangent of 1 is pi over 4. So we get 4 times pi over 4. So the exact answer is pi. And 3.13 is not great, but considering we used only n equals 4, we were accurate to 1 decimal place, right? All right, so moving into our next thing, what we want to talk about is error. If we have the integral from a to b of f of x dx, we can think of this integral in terms of the approximation plus the error. Or in other words, the error is going to be the difference between the actual value of the integral and the approximation. So in our previous example, our error would have been pi take away the approximation that we just got. So that would be the error in our approximation of that integral. So 0.0104, blah, 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 blah. And that's going to be our exact error for that integral. Turns out, exact error is very, very difficult to find, because it usually means you have to be able to find, as we were in the previous example, the exact value of the integral. But the whole point of numeric integration is that we don't know how to find the integral, right? So we can't directly compute the error using that formula. So it turns out, using some numerical analysis, we will accept these formulas as true. If you're really interested in where they come from, feel free to come talk to me. We can work through it. But we'll just accept them as true. If you take a numerical analysis class, they will beat this to death and a whole bunch of other ones. But it tells us that if we know the maximum value of the second derivative of the function, we can find a bound on the error. And when we say a bound, we know that the error is going to be less than or equal to this. For all we know, the error could be 0, but we know it's not any bigger than this. So when we don't know the actual value of an integral, the best we can do is bound the error. So it tells us the error in the trapezoid rule is bounded by k times b minus a cubed over 12n squared, where k is the absolute maximum of the second derivative. And similarly, the error bound for the midpoint rule is k times b minus a cubed over 24n squared. So according to these error bounds, how much more accurate is the trapezoid rule compared to the midpoint rule? So essentially the question we are asking is how many times, so x times e sub m equals e sub t, right? So solving that equation for x, we get x is equal to the error in the trapezoid rule divided by the error in the midpoint rule. If we were to divide these two things, we have a fraction divided by a fraction. Divided by k times b minus a cubed over 24n squared. So that's the same as multiplying by the reciprocal. And in this case, we'll notice a whole bunch of stuff reduces out. Yay, yay. And 12 goes into 24 two times. So the error of the trapezoid rule is going to be about half as much, or it's twice as accurate as the midpoint rule. So our error for those two, and if you look at the denominators, you'll see that. If I multiply 12 by 2, I get 24, right? So for this one, it worked out fairly well. So if we use those two rules, we're going to get half as much error with the trapezoid rule as we do with the midpoint rule. So basically, going from midpoints to trapezoids reduces your error by a factor of 1/2. All right, let's go ahead and use this to calculate some error. So going back to example number 1, how large should n be to guarantee that the error for the trapezoid and midpoint approximations are accurate within 0.001? So let's go ahead and use our formula. So the error for the trapezoid rule, as we just saw, is equal to k times b minus a cubed over 24n squared in absolute values. But ours is going to be positive. So the first thing we need to do is figure out what k is. And remember, k is the absolute maximum of f double prime. So we start with our f, and what's f of x? 1 over x. So f prime is going to be negative 1 over x squared, and f double prime is going to be positive 2 over x cubed. So f double prime, if we wanted to find its maximum, or its absolute maximum, what's our strategy? Well, we'd have to find f triple prime, find its critical numbers, and then also test the endpoints. In this case, if we take f triple prime of x, we're going to get negative 6 over x to the fourth. So this has no critical numbers, because f triple prime of x does not ever equal 0, right? So that would have no critical numbers, so then that tells us the absolute maximum has to be at one of the endpoints. So we would test f double prime of 0, which is, or f double prime of 1. So f double prime of 1 is going to be 2 over 1 cubed, which is 2. And f double prime of 2 is going to be 2 over 2 cubed, which is 1/4. So this is going to be the absolute max. And this is going to be the absolute min on the interval 1, 2. So what value are we going to select for k? 2, right? So our absolute max, so in our formula, k is going to be 2, and that's this value that we just found right here. We have our b and our a are 2 and 1, so our error is going to be 2 times 2 minus 1 cubed all over 24n squared. So our error is going to be, well, 2 minus 1 is 1, 1 cubed is 1, 1 times 2 is 2. So our numerator just simplifies to 2, and it's going to reduce to 1 over 12 n squared. So what do we want our error to be less than? So we want E sub t to be less than 0.000, was it 3 or 4 zeros? Just 3. 001, right? So we have 1 over 12n squared is less than 0.0001. Let's go ahead and write that as a fraction. Tenths, hundredths, thousandths, 10 thousandths, so that's 1 over 10,000. So if we multiply by our LCD, we're going to end up with 10,000 is less than 12n squared. Divide by 12, divide by 12. So 10,000 over 12, and we take the square root, is less than 10. So we grab our calculator, and if we take 10,000 over 12, and then we take the square root of it, we get this value. So since n is discrete, n has to be greater than 29, because you can't have 0.8 of a rectangle. That doesn't make sense, right? So you'd have to round up always the ceiling of whatever you get, right? So we would need 29 rectangles. So if we used n equals to 29, we are guaranteed that our error in that approximation would be less than 0.0001. And so that's only for n equals 29. So oftentimes, in many applications, this is how we're going to have to integrate things. But if you're talking about measuring something, if you make it accurate to 10 decimal places, most of the time we can't even measure things that accurately anyway, right? So that would be a good enough approximation without having to have the exact value. And if we can get 3 decimal places in this problem with only 29 rectangles, imagine with a computer and using 10,000 rectangles. You're going to be accurate to a whole bunch of decimal places. All right, so first things first, I had a typo below. So the error for the trapezoid rule has the 12 in the denominator. The error for the midpoint rule has the 24. So I wrote E sub t here. This was E sub m. So I actually did E sub m. Hopefully you guys did E sub t. But I just want to be very clear that these all should have been E sub m's. So that gives us the right number, but I grabbed the wrong rule. I wrote down E sub m and not E sub t, right? So now, let's do this one. If you did do E sub m again, you would have got the same number I did, which is good. But that's not what I intended, and that's my mistake. So let's make sure we write it down correctly this time. It's k times b minus a cubed all over 12n squared. So we want our error this time. We still know k is 2, so E sub t is going to be 2 times 2 minus 1 cubed all over 12n squared. So the numerator is going to be 2, and 2 goes into 12 6 times, so we get 1 over 6n squared. And we want 1 over 6n squared to be less than 1 over 10,000 again, or 0.0001. So we clear our fractions once again, and we get 10,000 is less than 6n squared. Divide by 6, divide by 6, take our square root. So we get 10,000 over 6, and our square root is less than n. So let's calculate that. So the square root of 10,000 over n, and we get 40.82. So n would have to be bigger than 41 in this case, right? Okay. Something else that I do want to mention is what happens to the error if I double the number of rectangles. All right, well, let's start with our E sub t is k times b minus a cubed all over 12n squared. Well, if I double the number of rectangles, that means n is going to get replaced with 2n, right? So my new error, E sub t, would be k times b minus a cubed over 12 times 2n squared. So k times b minus a cubed all over 12. 2 squared is 4, and n squared is n. So this is going to be, I can pull the 1/4 out, and then I have k times b minus a cubed all over 12n squared. Well, this is the original error formula. So if I double the number of rectangles, what happens to the error? The error is decreased by a factor of 1/4, right? So if you double the number of rectangles, you are going to decrease your error by a factor of 1/4. And that's because we have a square in the denominator, right? So if you double the number of rectangles, it's going to give you 4 times, because 2 squared is 4. All right, so the next thing we're going to talk about is called, well, we'll get to that in a second, what it's named. But so far we've done straight line segments to do all of our approximations. We made some trapezoids. But what if we do some tighter, better curve fitting? So what if instead of trying to connect the points with straight line segments, what if we pick the points 3 at a time, because 3 points will uniquely determine a parabola as long as they're not collinear. So what if we then picked a parabola that went through these 3 points, and then we found another parabola that went through these 3 points, and then another parabola that went through these 3 points. So each time we do that, we're going to be able to find the area underneath one of them. So let's see if we can develop a formula for what's going to happen. So let's imagine, and to make our math easier, we have a parabola that looks like this. Since our mesh is going to be evenly spaced, we'll make our width of our rectangles h, right? So we have negative h, 0, and positive h. That's our delta x. We're then going to have 3 points on this curve. Negative h, whatever y0 is, 0 and y1, and then positive h and y2. So we can come up with a system of equations for this. So we know our parabola in general is going to have the form y equals ax squared plus bx plus c. We can then do this integral from negative h to positive h of ax squared plus bx plus c dx. It is an integral on a symmetric interval, so any odd degreed terms are going to have integral 0 by symmetry, and all of the ones in the middle are going to get doubled, so all of our even functions. So this is the same as 2 times the integral from 0 to h of ax squared plus c dx. We then calculate this integral. We're going to have a over 3 x cubed plus cx, and we're going to evaluate that from 0 to h. So that's going to give us 2 times a over 3 h cubed plus c times h minus 2 times, and then these are going to be 0 plus 0. So we end up with our area being equal to 2AH cubed over 3 plus 2CH right now. We'll come back and work with that in a second. So that's our area, and we need to figure out some values for A, B, and C. Okay, so let's start with our system of equations that we're going to have here. So we have y of 0, that's this one. That corresponds to the input negative h. So if I put that in, I'm going to have a times negative h squared plus b times negative h plus c. So that gives me that my first equation, y0, is equal to ah squared minus bh plus c. Now let's move to our second point, y1. So that's this guy. y1 is going to be, when we input 0, so that's a times 0 squared plus b times 0 plus c. Well, that one works out to be y1 has to be equal to c. Right? And if we do the same thing with our last point, we have y2 is going to be a times positive h squared plus b times h plus c, gives me y2 is equal to a h squared plus bh plus c. So the goal of this is I want to eliminate a and c from what I have over here, right? Because I want to relate it back to the y values, which would be given in a discrete problem. So I have a system of 3 equations in 3 unknowns that I can solve to help me figure this out. So if, for instance, I take y0 and I add it to y2, so y0 plus y2 is going to give me, I have a ah squared and an ah squared, so that gives me 2ah squared. I have a negative bh and a positive bh, so they cancel. And then I have a positive c plus a positive c, so I get 2c, right? So now, if I add to that 4 times y1, well, y1 is c. That's the same as adding 4c. So then that would give me that y0 plus 4y1 plus y2 is equal to 2ah squared plus 6c. Right? And you're looking at this and you're like, seems like he's trying to cook something. I see this here, but I don't see that over here, right? We don't have the plus 6c. We do, it's just wearing a hat and a scarf. I can make that a fraction over 1 and then get a common denominator by multiplying the top and the bottom by 3. So that tells me the area is then 2ah cubed plus 6ch all over 3. I have a common factor of h that I can factor out, so I factor out the h over 3, and what's left behind is the 2ah squared plus 6c, which is exactly what I'm looking for over here. So substituting that in, I get that the area under each of those parabolas is h over 3 times 4, sorry, not times 4, times y0 plus 4y1 plus y2. So for any 3 points, P0, P1, and P2, I can find the area of the parabola underneath that curve by using that formula. I know, all I have to know is the y values. Well, when we're doing numerical integration, we know the y values, right? So that will allow us to do it for those 3 points. Well, if we can do that for those 3 points, we can generalize it to as many as we wish. Hence, Simpson's rule is born. So Simpson's rule gives us this pattern of 1, 4, 1. But when we look at Simpson's rule actually, we have our x, delta x over 3, that's this. The rule starts out 1, but then it goes 4, 2, 4, 2, 4, 2, 4, 2. That's because when we group up these points, y0, y1, and y2, the next group is going to be y2, y3, and y4. And then it's going to be y4, y5, and y6. So y2 is going to get counted twice. And that's where we get these 2's that are popping up in every other term. Because they're the ones that are they're the end of each of the parabolas. So they get counted twice. And that's why Simpson's rule goes 1, 4, 2, 4, 2, 4, 2, 4, 2. Because of the way we're doing this, n must be even to use Simpson's rule, or your parabolas won't line up. Your last one wouldn't have enough points. So we can only use Simpson's rule with an even n. Just the way it works. So the interesting thing is when we look at Simpson's rule error bound, in the numerator now we have b minus a to the 5th, but what's the power of the denominator? Instead of 2, it's a 4. So if you double your number of rectangles now, or your partition, what's 2 to the 4th power? 16, right? So if you double the number of rectangles using Simpson's rule, instead of decreasing your error by 1/4, you're going to decrease your error by a factor of 1/16, right? So Simpson's rule, those parabolas are much more accurate than the straight line counterparts, because they're going to bend and approximate that curve a lot better. All right, we're out of time. I do owe you an example of Simpson's rule, but it's really not that different from what we've been doing. I will do this